Okay, so we're going to go into some little bits of news. You may have occasionally, if you follow the news, you may have heard articles about faults opening up under roadways in Ethiopia and how East Africa will eventually peel away from the rest of the continent and become its own landmass. Yes, this is all true. True. So what we're going to focus on for the first part of this lecture is we're going to be looking at we've been looking at plate boundaries, and we're going to be looking at divergent plate boundaries. So I start off with this picture. This is from the Salton Sea. This is California's very own divergent plate boundary. I'll talk a little bit more about that later, but I'm going to show you a better example of this, starting with when we move our screen to the Google Earth. So if you look at East Africa, this is Ethiopia. Just zoom out a little bit for everybody. We are pretty much we're actually just about on the other side of the world from where my cursor is right here. But looking at East Africa, you notice that on the generally lush Ethiopian plateau, birthplace of coffee and many other wonderful things, and has this sort of like little tan gap through it of probably drier land. What you're looking at here is the East African Rift Valley, and the best surface expression of a Rift Valley any other place on the planet. And so what's creating this is your textbook case of divergent plate motion. I'll zoom in here. I'm going to pop up the vertical exaggeration a little. This very long linear valley. Sometimes there's rivers running through it, sometimes there's not rivers running through it, but the thing you really notice is just this long linear valley. And not only that, and it's also fairly wide. To give you a sense of how wide this valley is, let's use a useful unit like kilometers. From one side of this to the other is about 100 kilometers. So if you're standing in here, you might not even notice you're in this Rift Valley, especially for kind of a cloudy day. But this is your textbook case of divergent plate motion. So what you're seeing in this Google Earth image is literally the spreading apart of the Earth's lithosphere by the formation of new lithosphere at depth. So I'm going to put some arrows in here, annotate this, and boom. There we go. We're getting divergent plate motion here. These two places of the Earth lithosphere are literally spreading apart. Now, if we go at depth, and what I'm going to do here is put a little box in here. So imagine if you're taking a cross section of this whole feature. This all gives me a nice blank canvas to work with. What you'd see here is you'd see, first of all, quite a bit of faulting of the crust here. You see the there's probably a fault scarp running right along the base of this, each of these sort of edges of the valley here. Then when they contact the screen, these faults are probably going down quite some depth. There's probably a couple other faults within this valley. And by the way, this is horribly vertically exaggerated for your viewing pleasure. And your crust is getting thinner, and your crust, and in fact, entire lithosphere is getting thinner and thinner. Thinner. And as a result of the lithospheric thinning, you're starting to get you're starting to get some decompression melting of the mantle beneath you. Some of this is making its way to the surface, expressing itself as probably some of these volcanic features we are seeing in this valley. And so you're getting a couple interesting features here. First, you're getting faulting. Faulting. You're getting thinning, getting thinning of the lithosphere. 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 Then you're getting decompression, melting of mantle. We'll talk a bit more about decompression melting, but I always like to emphasize this early on because the more you hear this, the more plate tectonics in general and volcanism will start to make sense. As a result of this decompression melting, you're seeing volcanism at the surface. And so what you're looking at here is a textbook example of a continental rift or continental rift, and this is the first stage of a divergent plate boundary. Continental rift. We're going to save that right now. Boom. I'll have that popped up in the notes for you for your viewing pleasure. Then you're going to it's a little bit more what this might look like up close. You might see things like these linear sort of cracks in the ground if you're lucky. You don't always see these, but if you do see lots of linear cracks in the ground with lava coming out of it and you got this kind of symmetrical valley, that's a darn good chance. And the valley is very wide, wider than any river could be imaginable could make it. That's a good sign that you're looking at a rift valley. Nice other impression of what this looks like. Let's see. Couple other pictures of the spots. Yeah, here's another one. And yes, lava does come out of it. This is actually a volcanic feature. Here are humans for scale. And there it is. There's some unusual lava coming out of here. Not sure what people are doing here, but probably some geology. Yeah. Geology. So I'll take you on a tour of a couple of these in California next. So in the Salton Sea is actually a slightly more advanced stage of rifting than the Salton Sea actually represents what happens when your rift opens up and starts to form a sea. So here's what part of the African Rift Valley looks like from space, your on-land Rift Valley. Next, we're going to show you the Salton Sea. The Salton Sea is actually, believe it or not, part of a narrow ocean. So let's take you on a tour of show you what a narrow ocean looks like. 5, 4, 3, 2, 1. Okay, second valley type of feature, the one that you saw a little there in California, is your narrow ocean. So eventually what's going to happen is, and this takes a very long time to progress, but it does eventually happen if you keep stretching the crust, is that your valley is going to, your rift valley is going to be filled in with you're going to start getting oceanic crust from that decompression melting. At some point, you're going to completely rupture the continental crust. You're going to get oceanic crust. And so when you get that, you start getting features like this. This is the Red Sea of fame between Arabia and Africa. And a couple exciting things here. This is some interesting looking volcanic rock. Possibly. There are a number of volcanoes, by the way, in this. It's a fairly shallow water body. In fact, some of these have erupted within the last decade. Yeah. There you go. Here's an example of a beach composed of volcanic rock and mountains that are being uplifted. So what you're getting here is the beginning of a mid-ocean ridge. So if you were to slice under here enough, what you'd see in this picture, I'll zoom out just a wee bit, is the following. Five, four, three, two, one, action. So what you have right here, you still have your continental crust. You still have all those faults in your continental crust. Make this font just a touch smaller. Go back to the 24-point font. Brilliant. Yep. Still have your continental crust on either side of this. But now you have in the middle, you're starting to form, and you still have your decompression melt happening in the middle here. You still have your decompression melt of the mantle taking place in the middle. And of course, you still have your, and because of that, you still have your lithosphere, which we didn't put in the previous diagram, but that's okay. Still have your thinned out lithosphere that's thinning greatly away from here. You still have your decompression melt coming up here. But now that you've completely ripped apart the continental crust, what's happening is this decompression melt is making its way to the surface. And what you're seeing at the bottom of this body of water here is the beginnings of oceanic crust coming out. And so you're getting the formation of a mid-ocean ridge. And this crust is spreading away from, and so while these two pieces of continent are spreading away from each other and are still fairly uplifted, you might notice that the pieces of continental crust on the side of the sea are still uplifted because they're being held up by thermal buoyancy. Now your volcanism is focused at the little young mid-ocean ridge. Mid-ocean ridge, and of course we have mid-ocean ridge. Usually you have an ocean above it, and this mid-ocean ridge is spreading out and having fresh ocean crust being generated. Crust. And so the name for all this stuff that we're looking at, we're going to call it a we call this divergent plate boundary number 2, narrow symmetrical sea. Divergent 2, narrow symmetrical narrow symmetrical sea. And so this is kind of the textbook example is the Red Sea that you're looking at in this image and the sort of doctored diagram. And so these narrow symmetrical sea often have tall mountains around them because thermal buoyancy. Indeed, the highest point on the Arabian Peninsula is not very far away from here. Mount Sinai of fame is sort of deep in the background of this picture. And of course, you also have the highlands of Ethiopia, all connected with sort of thermal buoyancy of of the lithosphere being a little thinner and the crust being quite a bit hotter. All of these factors making it lighter, giving you these tall mountains. Hmm. 5, 4, 3, 2, 1. Action! So, the Red Sea is definitely your classic textbook example of this, but you also see this in California. This is the south shore of the Salton Sea. Now, this may not look like the mid-ocean ridge I showed you in the previous diagram, but there is divergent plate motion happening along the south shore of this sea. There is volcanism taking place, and this row of volcanoes known as the Salton Sea Buttes. There's also some mud volcanoes and other interesting things along the southeast shore of that lake. All these are. Now, the reason it doesn't look like your traditional mid-ocean ridge is that, another process is happening. You have the Colorado River not very far away, and all of this has been covered by river delta sediments. So one of the things you find in narrow opening seas often is lots of interaction between volcanic material and sediment that's sloughing off the continent, especially if there happens to be a river mouth nearby. Now, the third and final plate boundary is as you keep continuing to diverge, you're eventually going to open up an ocean. You're going to open up a full-fledged ocean. And in the middle of that ocean, you'll have a full-fledged mid-ocean ridge. So we're going to head over to Google Earth, and I'm going to show you a little bit more details on what those mid-ocean ridges look like in a little bit more intimate detail. 5, 4, 3, 2, 1. Action! So going out here, so we saw that we had the Red Sea as your narrow sea. At one point, this whole region of the Indian Ocean probably looked a little bit like the Red Sea. And what you see very prominently on the sea floor is this very brilliant mid-ocean ridge and a bunch of pieces of continental material that have been separated. As you fly around the world and zoom out, you realize that there's a whole network of undersea ridges that all look very much like this ridge in the middle of the Indian Ocean. Not precisely so, but differently. More importantly, you might notice that Madagascar and India are on opposite sides of this ridge. This might have explained why lemurs have inhabited both places, even though lemurs cannot swim very well. Now, the one I like to look at, just because it's the one that is the most relatable, we have, of course, actually like to look at a couple of these, and you can see that these ridges literally exist in every ocean basin. However, they do express themselves a little bit differently. Like in the Pacific Basin, you don't see quite as much scarring, in part because this ridge is a very fast spreading ridge and very produces voluminous volumes of stuff. And so, but you can see even the Gulf of California has a ridge system running up of it, and that the Salton Sea is pretty much the northernmost end of that ridge system. Now we're going to go over to the Mid-Atlantic Ridge. I'm just going to give you some more details about it. I might notice the scale on this thing is quite a bit further, quite a bit more zoomed out than our previous previous diagrams. So look at the mid-ocean ridge again. Let's take a look, see what we find. Okay, 5, 4, 3, 2, 1, action! What we're looking at here is the next third and final type of divergent plate boundary. By far, in some ways, the most common, because all divergent plate boundaries will eventually become mid-ocean ridges if they survive as divergent plate boundaries long enough. That's hopefully what you take away. So what you see here, and again, this is definitely vertically exaggerated, is you still have your decompression melt down deep here. You still have your oceanic lithosphere here, or oceanic crust, sort of like forming a very prominent ridge as the volcanism comes out of it. And this crust gets deeper and deeper as it cools and subsides. And there's two things causing the subsidence to take place from a mid-ocean ridge. One, the crust itself is getting cooler. Secondly, though, remember that the difference between the asthenosphere and the lithosphere difference. That is, the asthenosphere-lithosphere boundary is within the mantle, and it's a boundary not of composition. It is a boundary based on material properties. And so what happens is when mantle rock's very hot and near the surface, it behaves more like asthenosphere, whereas when it's cooler near the surface, it behaves more like lithosphere. So yeah, is the lithosphere is going to get thicker and thicker as you get further away from this mid-ocean ridge. So that this thickening is taking place with time, not time. So the faster your mid-ocean ridge spreads, the larger and broader your mid-ocean ridge is going to be. And here you have ocean crust. Ocean crust, and because by this point you've probably been erupting ocean crust long enough that the magnetic field has reversed several times, you're probably also starting to see some magnetic anomalies. So you're getting you're definitely getting magma and fresh ocean crust being extruded. You're also getting this kind of pattern of symmetrical pattern of magnetic anomalies. This is where you're getting your symmetric magnetic anomalies in the ocean crust. And remember that we are still at a divergent plate boundary, so the motion is going to be away like that, away from the center. But that at this mid-ocean ridge, there you go, again, volcanism at the mid-ocean ridge forming oceanic crust. So at this point, we've created a mid-ocean ridge and basically gone over all of the major types of divergent plate boundaries. In the next section, we are going to be going over convergent plate boundaries. Thank you very much, and